So this is going to be a supplementary recording in addition to the lecture number 23 that we had in the morning. So we were talking about the boundary condition for omega for a wall, and we noticed that we indirectly supply a boundary condition for omega by using the definition of omega using the expression for omega in terms of the stream function, and we came up with this first order boundary condition which has a truncation error of the order of delta y. So it's a first order boundary condition that we have come up with, which supplies the boundary value for omega, that is omega b, in terms of interior and boundary values for the stream function psi. So we'll assume that psi values are known everywhere, and then we can apply a Dirichlet boundary condition for omega on a wall. So this is the first order boundary condition. Typically we would want a higher order boundary condition so that our overall scheme would be of a higher order. So let's talk about higher order boundary condition for omega on a wall. So in the expression for a psi interior that we had written here on the top, we can include another term in addition to this delta y squared term. We'll include another term which is a delta y cubed term, and that will allow us to obtain a higher order boundary condition in this case. So let me write the expression for psi interior again. Right, so this is the expression for psi interior. Again, this term goes to 0 because this is nothing but our x velocity, and on the wall x velocity is 0. And then for the third derivative of psi with respect to y, because remember that we want to use this term in obtaining the expression for omega b, because omega b is nothing but, let's look at it here. So omega b is nothing but minus the second derivative of psi, partial derivative of psi with respect to y on the boundary. So we want to write this term in terms of all other terms. So we do get a third derivative. So the way we deal with this third derivative is we can write the third derivative. So let's write so this is the basically del by del y of omega on the boundary, because omega on the boundary is del 2 psi by del y2. So this is nothing but del omega by del y for on the boundary. So we can replace this term. So I'll just do it here, or let me just write it below it. So this is minus del omega boundary by del y. Or rather, let's write it this way. It's much clearer. Right, so we can now substitute this into the expression for omega on the boundary. So omega on the boundary becomes, well, we also have del omega by del y term, so we'll keep it on the left hand side because these are the unknowns. So the only difference we have as compared to the terms above is that this time this expression that we had earlier is still there. So minus 2 by delta y squared, the minus is now taken inside, so it becomes psi b minus psi interior. And then we have an additional term, which is this one, which is coming from the extra term that we have included here, which is this one. So what I can do is to write del psi by del y, which is written on the boundary. So I can use a backward difference. So I can write del psi by del y as del omega by del y, which is this one. So I can write this as omega on the boundary minus omega interior upon delta y. Okay, so this allows us to now develop a boundary condition for omega, a higher order boundary condition for omega. And this time I'll neglect these truncation error terms because they are not included in the expression. Okay, so we can rearrange the terms, and this gives us 2/3 omega b plus 1/3 omega interior is equal to twice psi b minus psi interior upon delta y square. Okay, so this is a higher order boundary condition for omega on a wall which is a non-permeable no slip wall. Okay, now you may question that we are trying to write a boundary condition for omega, but here we get an interior point as well. So how can we write this? How can I write the expression for omega b in terms of an interior point? Will this result in an implicit sort of expression? Actually, that depends on how we deal with these points. So if you have already calculated omega interior in the loop in an explicit, let's say, expression in an explicit algorithm. So in an explicit algorithm, and that is the one we'll be using in the lab, which is going to come soon, because we are interested in the steady state expression for omega and psi. So in an explicit algorithm, we will first visit all the interior points. So omega interior has already been calculated. And the next thing we'll be doing is we'll be calculating omega b. So when you apply the boundary condition for omega to calculate omega b, omega interior is already known because of the way we are dealing with the algorithm. So let's make a note of that here. Although I'll write the algorithm for the explicit algorithm for this omega psi formulation, but let's make a note here. So in the explicit algorithm, omega interior would be known at this stage. Okay. So first the interior points are calculated and then the boundary points are calculated. Okay. Now the other thing is, one of you had asked me in the class very rightly that we are writing omega in terms of psi. So if we now give the time superscript, so we are trying to calculate omega b at the n plus 1th time. That in the explicit algorithm we are doing a time stepping, so we want to calculate the omega boundary points at the n plus 1th time, and this is written, let's use it for the same case. So we have 2/3 of this plus a 1/3. This is written in terms of the psi values, but at what time? Well, at the same time, because omega is written in terms of psi for the same for the same time. So this becomes omega b at n plus 1 minus psi b at n plus 1 minus psi interior at n plus 1. But the n plus 1th values for psi are not known yet, because the way algorithm works is that first you calculate the omega values, first you visit the omega equation to calculate the omega values using the velocities u and v, and then you calculate the you visit the stream function equation, because stream function equation has a minus omega on the right hand side. So the omega should be known and then we can calculate the stream function values. So we are stuck here in a loop that how do we work this out. So in this case what we do is, since we are dealing with an explicit algorithm which particularly for a steady state solution, so we can use the nth values for psi. So we can in fact say that I'll just circle here and say use n values instead. But there is a note here that using the nth time value is incorrect, except when we are using this transient approach or a false transient approach for calculating the steady state solution. Right. Now what would we do if we really wanted an actual transient algorithm, not a false transient, if you are interested in the intermediate time values of omega and psi? In that case what we do is we basically and I'll discuss that when we talk about the algorithm, but we repeat the steps. So you would use you will solve the omega equation and first, and then you will be using the psi at the nth time, because that's the only thing we can do, and then you solve the psi values, you visit the psi equation, you solve the psi values, and then you sort of repeat it again. Now you try to solve the omega equation again. So it's like you do multiple iterations until the psi values that you have on the nth you're not time stepping, we're still calculating the omega n plus 1 values using omega nth time values in an explicit algorithm, but every time we have a better estimate for psi, because we have done one iteration. So psi values have improved, and ultimately we'll after a few iterations we'll see that the psi values that we are using are actually the n plus 1th psi values. Okay. So I'll discuss it with you when we talk about the algorithm. but in the way that we'll be using in the lab, it's okay to use this psi nth values on the right hand side only once, and then you can move to the next time step. You don't need to do multiple iterations within a time step in this explicit algorithm just to ensure this right hand side boundary condition, or the right hand side of the boundary condition for the wall. Alright, so the next boundary condition we'll talk about is for the boundary condition for the stream function psi. So let's cover the wall boundary conditions first. Now we know that walls are psi equal to constant lines, so they are streamlines because the flow does not cross the walls or the streamlines. So the choice of the value of psi on any one wall or anywhere can be arbitrary, and then everywhere else the value of psi is in relation to that, because ultimately it's it's the difference of the psi that matters in the sense of the flow rates, the way psi works. So we'll not discuss more about it for now, but so you can choose the psi value at any wall to be arbitrary, and this can be 0, so that defines a reference, and everything else is in relation to that. And in psi equation anyways we have the second derivative of psi, so the difference is what matters. So let's choose for our case, for the backward facing step problem that we are dealing with, let's choose the psi value at the lower wall to be 0, and again that is arbitrary, our choice of psi equal to 0. But then once we choose the psi equal to 0 at any point on the lower wall, then the complete streamline, which is actually this complete surface, is going to be psi equal to 0, and everything else is going to be in relation to this psi. Okay, so this it becomes so we'll call it psi, so we'll say choose psi on the lower wall to be 0, but the choice is arbitrary, it's a choice of reference. Okay, and then the upper wall, then because we're talking about walls here, the upper wall has to be in relation to this value for psi at the lower wall. Now we know that the difference between, so let's call it psi upper. So we know that psi upper minus psi lower is equal to the discharge or the volume flow rate q dot. Okay, so which will be known because you know the inlet velocity profile, so you know the flow rate as well. So this will allow you to choose the value of the psi at the upper boundary. So q dot is a known value, at psi at lower is 0, so this implies that psi at the upper wall is going to be q dot, because we have chosen psi lower to be 0. Okay, so we talked about the wall boundary conditions for both omega and psi. So now next comes the inlet and the outlet. Okay, so let's since we are continuing with the discussion on psi, so let's talk about psi only, and then we'll move to omega. So inlet boundary condition, we can also call it an inflow. Inlet is where the flow enters, so we can also call it inflow boundary condition. Right, so for psi, now psi is defined now on the inlet boundary condition. We know that we know the u profile. So u is a function of y. In fact, since we are using a parabolic profile in our problem that I discussed in the morning, because the laminar flows will have a parabolic profile for a fully developed flow profile. So think of it as a long inlet pipe. So we're just interested in what the inlet velocity is when it enters this backward facing strip. So if there was a long upstream pipe, then it would have given it enough time or distance to become fully developed, which is the parabolic profile. So this parabolic profile can be written as the u velocity at x equal to 0 and at any y as u naught times y upon L times 1 minus y upon L, where L is the width of the inlet or the diameter of the inlet channel. We'll call it a width because this is a two-dimensional problem, so that is L. You can check for y equal to 0. This now remember this y is taken from this point at the bottom. So for y equal to 0, we get u equal to 0. That's the bottom point, and on the top we have y equal to L. So this again becomes u equal to 0. And at the center where we have y equals L by 2, we get u naught times half times half, so it is u naught by 4. So that's the center line velocity. Okay, and u naught I think is the average velocity here. So this is your inlet velocity profile, and that is known, that will be given to you because you told it's a parabolic profile. So this is how the parabolic profile looks like. So how do we calculate the value of psi from here? Now we know that u by definition is written as del psi by del y. So this means that psi can be written as integral u dy, where and in fact since we are calculating psi because on the inlet you will want to know the psi values at any arbitrary y value. So psi will be a function of y. So psi as a function of at the left boundary as a function of y is integral the expression for u, whatever we have, which we have written. Now since we are using the y coordinate, so we are integrating, so I'll call it y tilde times dy tilde, where the y tilde goes from 0 to any arbitrary value y. So y here is a coordinate which is used for where the value of psi is being given, and y tilde is just a coordinate that we are using for integration. So I'll let you calculate the integral yourself and simplify. But please do that because you'll be needing that for the lab. So this was inlet or inflow boundary condition for the stream function psi. Let's talk about the outflow or outlet boundary condition. So typically the boundary condition outlet is a tricky business because there is no strict boundary condition available for the outlet, and there are many different options available that you can try, but the most common one that we use, since the flow is happening from left to right in this backward facing step, and assuming that the backward facing step is long enough, so we say that the psi value does not change with x. So it's like a fully developed condition. So one option is that you use del psi by del x is equal to 0. So that's like a fully developed condition. So, okay, so there is no correct boundary condition available for the outlet. So we have to try various options. So this is the most commonly used. Now another one we can have, which actually is mathematically incorrect, but it still works for some reason, is that we can use del v by del x equal to 0. So we are saying that the y velocity, which should not be there, but still we say that the y velocity, which is v, is not changing with x at the outlet. And this basically means that because v is del psi by del x, so this becomes del 2 psi by del x2 is equal to 0. But that's the second derivative. Now remember, we told that boundary conditions are typically supposed to be lower order than the governing differential equation, otherwise it does not help us. So this is, I would recommend not to use it, although it does work in some cases, but recommend to avoid, as boundary condition order is same as governing differential equation. Okay. So I'll just make a note here that there is no correct So this is where the experience with a given problem comes into the picture. Now another thing that you may want to do is to apply a Dirichlet boundary condition for psi. Now what we have applied are Neumann conditions, for example, the derivative of psi is given, but Dirichlet could be very wrong. Okay. Unless your L3, the length of the channel is extremely long. So I would suggest don't even never go for Dirichlet. So Dirichlet boundary condition at outlet could be very wrong. Do not try this. All right, so these were the outlet or outflow boundary, inlet and outlet boundary conditions for the stream function psi. So the next thing we'll want to discuss, and that is going to be the last thing because we've already talked about the walls, is going to be the inlet and outlet boundary conditions for the vorticity omega. So let's start with inlet boundary condition for omega. So omega is defined as del v by del x minus del u by del y. Now at the inlet, what we see is that the velocity that is supplied is in the x direction, so that's u completely. So at the inlet there is no v, well, that may not be a correct argument, but the rate, the derivative del v by del x at the inlet is much smaller in magnitude as compared to del u by del y. These are the ideas of scale that we are scaling that we do, that we to compare the terms. So we'll say that we'll neglect this as this is small in comparison to del u by del y at the left or the inlet boundary. Okay, so at the inlet it's the u that changes significantly with y as compared to the y velocity, that is v, with respect to x, right? So omega at the inlet is minus del u by del y, and u profile we already know, u as a function of y, we just wrote that. So we can calculate omega easily using the so this can easily be computed using the inlet boundary condition for y, for u. Using u as a function of 0 comma y, that is at the left boundary. So x equals 0 is the left boundary, or the inlet boundary. Okay, so this way omega inlet becomes a Dirichlet boundary condition, because its omega inlet is a known value as a function of y, of course. Okay, then outlet, well, I'll simply use the fully developed condition. So del omega by del x is equal to 0. Again, the same ideas work for omega as well, as we have discussed for the outflow boundary conditions, but safest to start with del omega by del x equal to 0. Right, so this completes our discussion on the boundary conditions. So now we know how to supply boundary conditions for both omega and psi for the walls as well as inlet and outlet. Right, so a couple of other topics which may not be necessary for the lab, but which are quite useful in general for engineers. One is that in engineering we are not really interested in knowing the velocity field, although it's good to know that, because then you can calculate a lot of things from there. But we are typically interested in things which are integrated quantities, such as drag of different types, friction drag, form drag, or the pressure drag, or lift, and so on. Okay, so these quantities are of interest for mechanical engineers particularly. So rather than calculating the velocity field and then using that, if there is a way to write the expressions for these integrated quantities such as drag in terms of omega and psi, that is much useful. Because omega and psi are directly calculated in our program, so we can use those values to calculate these quantities. So let's look at a couple of them. So we call it integrated quantities because they are calculated as a sum or an integration of the local field variables such as u and p. So let's take now it could be friction drag, which is prominent, for example, in aerodynamic bodies, where the pressure drag is not well, it exists, but the friction drag can actually become quite prominent if it's highly aerodynamic, because then the surface effects are much more prominent. So friction drag or pressure or form drag are a couple of examples. So let's talk about friction drag. So friction drag is given as in terms of the wall shear stress. So for any surface which is a wall, a solid surface, there is a wall shear stress, and when you multiply that by the surface area, you get the friction drag. So you have to integrate the wall shear stress over the complete surface area to get the friction drag. So friction drag is given in terms of wall shear stress. So tau wall is useful for calculating friction drag. Okay. So tau wall by definition is given as the dynamic viscosity mu times del u by del y. I am assuming that the wall is at x equal to constant surface, so the normal direction is y, or even if the wall is curved, you can always define y to be a normal coordinate. So that's del u by del y at the surface of the wall. So this is what, so we need to calculate del u by del y on the wall. So this can be done from a velocity profile, but velocity profile is obtained from stream function values and so on. So let's see if we can use those quantities directly. So what is omega, which is the vorticity on the wall? So this is given as by definition del v by del x minus del u by del y on the wall. Now del v by del x on this x equal to constant wall is 0. That's because v is 0 on the wall. It's a non-permeable wall. So in that case del v by del x is also 0. So this quantity is 0 because it's a wall on wall. Okay, del u by del y definitely is not 0. That is what we want, but so del u by del y can be written in terms of omega value on the wall. So it's simply minus of that. So wall shear stress basically is minus mu times omega on the wall. Okay, so omega on the wall is something that we have calculated as a part of the solution, so we can use that to calculate the wall shear stress. Well, just supply the value into to get the expression for wall shear stress, and that can be integrated over the surface. The other thing is another integrated quantity or a local quantity you may, well, it's not an integrated quantity, it's a local quantity called pressure drop. So pressure at different points is what you need to calculate pressure drop, and that will give us the drag on the body. So that's the drop of pressure between 2 points. So that is the net force on the body because of the fluid. So how do we calculate pressure drops? For that we have to calculate the pressure values. So one way to do that is, as we discussed earlier, is to solve the pressure equation, which is the pressure Poisson equation. So you take the divergence of the u equation, you take the divergence of the v equation, you take the x derivative of the u equation and add it to the y derivative of the v equation, which is basically taking the divergence of the vector form of the momentum equation. But that is best avoided to solve, because solving pressure Poisson equation is actually quite expensive. We'll discuss that later when we talk more about the predictor corrector approaches and so on. But I would want to avoid that because I can actually calculate pressure drop in a much simpler way. So in a simple flow where you have flow in a pipe, you'll want to know the pressure drop because that's going to be that's going to tell us how much of a pumping power we need for the fluid, for example. So one option is to solve a pressure Poisson equation, but it is best avoided. I'll not go into the details of that, but just accept my word that it is best avoided. So, but there is an alternative approach. So let's talk about that. So let's write the u equation on the wall. No, bottom wall. So u equation was del u by del t, that's a transient term, plus u dot grad, where u vector is the velocity vector and small u is the x component of that. So this is the u equation. Now on the wall we know that the u component and v component both are 0. So that means this goes to 0, it's a wall. Well, this is also 0, it's a wall. So these two terms are 0. Let's look at the right hand side. Of course del p by del x is not 0, that is what we are interested in. In these situations we assume that p variation with y is not that important. So it's P primarily varies with x, and you may recall the discussions that you have seen in your fluid mechanics course. So we'll not go into the reasoning behind that. So P is only a function of x in this case. So then let's look at the diffusion term, or the Laplacian term, which is del 2u by del x2. Now since u is 0 on the wall, and the wall is at along the x direction, so del 2u by del x2 is also 0. So we are only left with the second term, del 2u by del y2. Now that is not 0 because u varies with y. Even on the wall, just as you go above the wall, there is a sometimes significant change in the value of u. So we can summarize or simplify this as del p by del x is mu, because we kinematic viscosity is dynamic viscosity by rho, so the rho cancels, times the second derivative of u with respect to y on the wall. So these are on the wall, these quantities, because you've written the u equation on the wall. Right. Now what about omega on the wall? Omega on the wall was given as, we just wrote that as minus del u by del y on the wall, del v by del x was 0 because v was 0 on the wall. This is an x equal to constant wall. So this allows us to write del p by del x on the wall as mu times the second derivative of u with respect to y becomes the first derivative of omega with respect to y. So del omega by del y on the wall with a negative sign. Right, so this is the del p by del x. Now from here you can calculate the overall pressure drop. So this is the pressure gradient at a given point. So from here we can simply integrate. So we can calculate, I can integrate this, I can calculate p at any x minus p at let's say some reference point is integral going from 0 to x times dx. Now I'll call it dx tilde because I'm using x as the variable on the left hand side. And this del omega by del y, which is what we need inside the integral, can be simply obtained from the solution of the omega equation. So okay, so this is how simple it is to get the pressure drop. All we have to do is, since we already know the omega field, we can calculate del omega by del y. It is on the wall, remember, it's on the wall. So we just take one point above and the wall value and take a difference, divide by delta y, and then that gives us the partial derivative. They can substitute that inside the integral. Integral will become a sum and so on. That can be discussed better when we discuss this in the code. Okay, so just a note here that when you'll be calculating the pressure values. Now pressure for an incompressible flow situation is always relative. So we can supply, we can as we did for stream function, we can make the pressure value to be a fixed reference value at some point, and then everything else is in reference to that pressure value. So typically we'll sometimes say that at the outlet the pressure value is P equal to 0, and then everything else is in relation to that. But that's again arbitrary choice. You can choose any pressure value to be a reference pressure value. So one intuitive reasoning for this is because in the equations of u and v, you have the gradient of pressures. You don't have pressure term. So it's just the pressure difference values that comes in the equation. So there is no reason for the absolute value of pressure to be something in incompressible flows. But for compressible flows, because of the thermodynamics relations, pressure has to be supplied. Pressure is not relative, it's absolute. So pressure in incompressible flow is relative to a reference which can be specified. Again, this point, it's quite important, but it's best discussed when we see computer programs. So that completes our discussion, supplementary discussion. Now I'll go back to the lab problem, which is the backward facing step that we discussed in the morning. So let's go to that. So let me copy this and then we'll continue the discussion. Right, so in this lab problem, we have to solve for a steady state solution. So let's discuss it in a bit more detail. So I'll supply the values for the geometry parameters such as L, L2, LC and L3. These four values will be given as a part of the problem. So next is you will have to calculate the steady state solution. Using the omega psi formulation, because it's a 2D problem, so you can use the omega psi formulation. So what will we do with the formulation? One is we will want to visualize the flow, so you'll have to plot the velocity field. Now, usually what we do is, even experimentalists, what they do is from their experiments, they'll want to see streamlines. Now, for us, that's very easy because we are using a vorticity stream function approach. So we have already calculated psi field. So we can easily plot the psi values, and the contours of psi, which is basically psi equal to constant lines, are nothing but streamlines in this case. Okay, so from the steady state solution, when you plot the contours of psi, we can plot streamlines. But streamlines will not give the direction of velocity, they just give the lines, although we know the direction intuitively. But there's another thing called velocity field, which is the technical term in plotting is called a quiver plot. It's basically a vector plot of velocity field. Okay, so plot velocity field, then streamlines. So these will help us visualize the flow field. So these are local variables because they are plotted at every point. Now the other thing is to get some integral quantities. Now one thing you will want to know is the value of the recirculation zone, that is LR. So how do we know the value of LR? Of course we know the velocity field, One way to do it is to calculate um, the shear stress on the wall. So what happens is that the direction of flow um, just above the surface is so if you look at the recirculation zone, just to the right of the recirculation zone, just above the wall, the flow is to the right, and just on the left of the recirculation zone boundary, the flow just above the wall is to the left. Okay. So if you were to plot the shear stress, so shear stress is going to change direction if you plot the shear stress as a function of x along the bottom boundary. So we plot tau wall, which is a local quantity, is a function of x on lower wall. So wherever it changes direction from negative to positive, because it's applying a negative shear to the left of the recirculation edge and it's providing a positive shear, so it will become 0 at the edge. So that's the easiest way to calculate the LR, the recirculation zone length LR. Okay, so these are the things that you will be expected to plot. So from tau wall, you can use the same ideas that we discussed just a couple of minutes ago on using the omega values directly to get the wall shear stress. So what is the algorithm of that we'll be using? So we'll be using an explicit algorithm. So what that means is, because your omega equation is a transient equation, you have del omega by del t term. Although we want a steady state solution, we'll still be using a transient equation. So we'll be doing a transient solver using an explicit algorithm, and we'll keep doing this until the solution stops changing. That is, the omega values and psi values, they stop changing with time. So we'll stop time steps after that. It's a very common approach, and since we're not interested in the initial values, so we can still use our approach of omega on the balls specified in terms of psi at the previous time step. And you can also use alternate direction explicit and all these approaches, which are not very good for calculating the transient solution values, but they are good for calculating the steady state solution. Now for this equation, since we are interested in steady state, you could formulate the equation in such a way that del omega by del t term was not even there, because steady state means that there is no change with time, but we will still keep that. Okay. Now the question is, then what do we start with as an initial condition? So that is irrelevant. So you start with any omega value, and don't take it as a very large number, but you start with any omega and psi value. Omega value, psi is calculated from omega, so you can start with, in fact, start with any u and v values, and then you will see that the steady state solution will not be dependent on the initial condition, because that's by definition the situation where it stops changing with time. So that time del omega by del t term vanishes altogether. So it should not be, the steady state solution should never be a function of time, because the time term is not even there in the equation. So use explicit equation with any initial condition for u and v. So easiest one to do use is you start with u equal to 0 and v equal to 0, but that may not be give the fastest convergence. Rather, if we supply u equal to the inlet parabolic profile everywhere, because the flow will be moving from left to right. So it won't be 0 in the final state. So the closer we are to the steady state solution, the quicker it will be in terms of the number of time steps we require in the explicit algorithm. So we'll use an explicit algorithm with any initial condition for u and v, and we'll continue this until we get convergence. Okay, so let's write the algorithm formally. So assume arbitrary initial conditions for u and v. So we'll call it u naught, v naught. So naught is basically n equal to 0 the first time, or the 0th time, and then from here you can calculate omega naught and psi naught. So omega naught and psi naught are dependent on u and v values. We already know how to relate omega and psi to u and v. So this is the first step. Next is our time loop. So we time step the omega equation. So that is, we calculate omega at the next time step, that is omega 1 or superscript 1 for all the interior points, as well as the boundary point. So with boundary conditions we have to get. So to get omega n plus 1 using, let's write, using explicit methods are very easy to program. Okay. You can simply write omega n plus 1 in terms of all the nth time values. Next is the stream function equation. Again we solve it with the boundary conditions to get psi at n plus 1th time. I'm using n plus 1th because this loop is going to repeat. Then the third step is to get u and v components from the psi values that we have just calculated. So u n plus 1 is simply del psi by del y at the n plus 1th time, and then v n plus 1 is del psi by del x with a negative sign, sorry. So we calculate these, and once you have done that, once you have u n plus 1 and v n plus 1, now we can repeat this. So we'll call it as step number 3. So n equal to n plus 1 means that now the n plus 1th times values are put in the old values, and then we calculate the next time step value. So we repeat step 2, but until what happens? So until we reach a steady state. So we say repeat step 2 till steady state is obtained. So we need to supply a check for steady state. So steady state check is steady state check for omega. Now you can check for all the fields, but if omega reaches, then because psi is dependent on omega and so on, so that will also reach a steady state. Because if psi is not changing, then if omega is not changing, then psi will also not change. Okay, so steady state check is going to be omega at the next time minus omega at the nth time, and then for what point, because you have all the grid points in the domain, and each one will have different values for omega at n and n plus 1th time. So we use this 2 norm as we had discussed, or we use all called the RMS value. So we square the difference, sum it over all the interior and the boundary points, and then we take a mean and then take a square root, and that should be less than some epsilon tolerance, okay, some epsilon which is a small number. Now, one thing to note here is that this change in omega can actually be quite small if you choose a very small delta t, because delta t, that time step size that is our choice, of course that will be dependent on some stability criteria as well. But if delta t is very small, even if we haven't reached steady state, the change in omega will be small. Okay, so it could happen that we may wrongly interpret that omega has this equation has converged, or a steady state has been reached, although it is not the case. So what we do is we always normalize it with the time step. So if you have a large time step, then chances are that the difference of omega will be large if steady state has not been reached, and if time step is very small, then you divide by that small time step, so that amplifies the small change in omega for this check. So I'll typically we'll use this as 10 to the minus 3 or 10 to the minus 4. So 10 to the minus 3 is good enough. So these things again come with experience. So one other thing that is done is we haven't talked about actually about that is what is the delta x and delta y, what are the delta x and delta y values, or what is the number of grid points that we'll have. There is something called so this is the end of the algorithm. There's something called a grid convergence test, grid convergence analysis, grid independence test, and so on. So they are all the same thing. So grid convergence test is that we plot the solution at any point in the domain. So let's call it omega at some point p as a function of the number of grid points. So you will start with a very coarse mesh, so the number of grid points will be small. You will have some omega value at the p point. P is some point in the domain, and then as you increase the number of grid points, so this each point on the x-axis is a new simulation. So as you do that, you will see that this omega p initially for a very coarse mesh, it may fluctuate, but then you will see that it will start to flatten out, and then after some point the change in the solution omega p that you are getting will be very small as compared to the work you have to do in terms of adding more number of grid points and doing more computational work. So we say that around this point the solution has become independent of the grid size, although that's not exactly the case, but relatively. So we say that we will so beyond this solution is grid independent. So there is no benefit, another significant benefit. There is no significant benefit of choosing delta x and delta y values which result in number of grid points beyond this number. Okay, so it's always good to do this analysis, especially if you are doing some parametric study. In a design problem, you will want to solve a simulation for different design. That design parameter could be the fluid property that is being changed that you're testing, or some design of the solid pipe, or it could be even operating conditions. So you'll want to optimize something, right? To do that, what is the number of what are the number of grid points you choose? If you choose a very coarse mesh, your solution may be inaccurate. So then it's not a correct or not a good solution that is being obtained from CFD. But if you choose a very fine mesh, then you basically are wasting your resources, which ultimately translates to cost. So once we have chosen this grid size, then we can run many more simulations in our production problems. Okay, so this grid convergence test is something that you'll be expected to do as a part of this lab. Right, so we'll stop here now, and Next is you will see the lab as a Jupyter notebook. In the lab we'll have two parts. One is the backward facing step, where most of the code will be provided with some blanks that you have to fill based on what you've discussed in the class. So that's not a completely specified code. You'll have to fill in some parts. I'll give you the solution you expect to get, so that you know if you're doing things correctly, and it will have all these plots that you have to, it will generate all these plots as a part of the problem. And part 2 of the lab, which is going to be an assignment, is to do the same thing for a different geometry and a different set of boundary conditions. Okay, so we'll stop here, and then I'll meet you after the vacations.